Section 2, Part B, or Part 2, whatever. Now I want to talk about spreads, and in particular I want to talk about the rest of the things that are in the order scheme of things. So start off with some general remarks I've already made here. For spread, we can either use the interquartile range if we're in the order scheme of things with median, or the standard deviation if we're in the balance scheme of things with mean. You never want to mix them up. It doesn't make sense. You're either doing a form of analysis based on where things fall in an ordered list, or you're doing a form of analysis based on how things balance out. Which scheme is the better scheme? Generally speaking, the balance scheme of things has the prior claim, unless there are things that are radically asymmetric outliers that could throw things off. So, for instance, if you have a symmetric distribution, it doesn't matter. We call it the median. So we call it the mean. The mean is more important than the median, and the mean is generally our first stop. We only use the median. We only resort to the order scheme of things when the mean scheme, the balance scheme, would be misleading. In other words, as long as things are not very asymmetric, we tend to stick with the mean. So the fact that this line is the mean and the median, but the fact that it's the mean is a little bit more important, is what I'm saying. So, on the other hand, if things are very asymmetric, then we tend to use if they're skewed, outliers, anything that might throw off the mean, then we go with the median. But the mean does have the prior claim. For instance, whenever we give you a practical example, everybody always wants to know what was the average on the exam. And the answer to that question is always the same thing. You don't care. It doesn't matter what the average was on the exam. Are you really interested in how a couple of people who got zeros or 20% are pulling down everybody else's grades? No, what you're interested in is the median. You want to know the spot in the list where half the people did better and half the people did worse. That's the median. What is the grade that cuts off the small half from the big half of the class? If there's 40 students, what's the grade where 20 did better and 20 did worse? The median. The median grade is the thing you really want to know. And remember, grades tend to be very left skewed. Probably most of them are in 70s, 80s, 90s, and then a very few are very far away. So the skewness means that you prefer the median. On the other hand, incomes, annual income, let's say, tends to be very right skewed. Not a lot of people make a very big amount of money. They make sure of that. So, because it is so skewed, you prefer to talk about the median income rather than the mean income. The spot on the scale where half of the people make more and half the people make less is more important than how everybody's salaries balance out, you see? Of course, it's all about the context. If you see a journalist saying that it's shocking that half the people in the country make less than the median income, well, congratulations, you know you're dealing with a moron, because that's what median income is. It could not be otherwise. So it's all about the context. Some have one use, some have another. But generally speaking, as long as things are not very asymmetric, we tend to stick with the mean. The mean and the standard deviation will be important for the rest of the course. The median and all of his cousins, not so much. Nevertheless, it's where we're required to be at the moment. Oh, by the way, I probably should have done an example of the even case as well here, right? So when you're computing median, like I said, it's either the middle one or the average of the middle two. So for instance, if you have 10 numbers, then 1, 2, 3, 4, 5, that guy, 1, 2, 3, 4, by that guy. So in the odd case, having ordered the list, the median in the odd case is the middle one. In the even case, it's the average of the middle two. 8 plus 10 divided by 2, 9. Now, for this particular set of data, it is literally true that half the numbers are less than 9 and half the numbers are more than 9. However, for the casual observer, you could say the same thing about 8.5, right? Nevertheless, this is the way we compute median in the even case. It's the average of the middle two. 8 plus 10 divided by 2. So, sorry about that. Should have done an example of an even case. Now, oh, sorry, that's page 1. We did that. So, page 2, that takes us to about here. So, having used now we're still in the order scheme of things. So, having used the median to break the set of data into halves, then we can find the median of the small half and the median of the large half. And of course, these are going to be the 1/4 point and the 3/4 points in the list, right? So that's the idea. The technicalities we'll talk about in a second. The first quartile, Q sub 1, is the median of the small half. And the third quartile, Q sub 3, is the median of the large half. This is the 1/4 point in the list. This is the 3/4 point in the list. Q2, of course, nobody talks about Q2, the second quartile, but, the 2/4 point in the list is the half point in the list. The Q2 is just another way of saying median. Nobody does. So, with the understanding that we can find the median of the small half and the median of the large half, all that we really want to be clear on is, number one, how to compute median. We know that. We talked about it. It's the middle one or the average of the middle two. And then number two, exactly what do we mean by the small half, the large half? We want to all be on the same page with the numbers that we use. Now, these rules are not 100% standard. I would not advise doing quartiles in Excel. They use a weighted system that nobody really understands, not even the programmers, and they're kind of in a world all their own. But for an elementary statistics course, even for an elementary statistics course, all of the books we use are not 100% agreed on the quartile rules. The closest thing we have to a standard, some books do things in different ways, so if you've seen this before, my sympathies. Some books do things in different ways. The rules are not 100% standard, but the following, what we're going to do, is the closest thing we have to a standard. I've seen every variation possible on these rules in different textbooks, but the following is what we're going to do, and it's the closest thing to a standard. If you've got a TI type calculator and you know what buttons to push, it is the same rules it will use. In the odd case, don't use the middle one. In the even case, use each half. So for instance, if you have an even case, then everybody's over here is going to get used for Q1, everybody over here is going to get used for Q2. On the other hand, if you've got an odd number, then don't use the middle one. If you've got 11 numbers, then 5 over here for Q1, 5 over here for Q3, and don't use the middle one. So in particular, in the odd case, the middle one does not get used. In the even case, each of the contributors to the median gets used in his respective half. So this means we've got 4 cases. Odd within, let's get it in order here. Even within even, odd within even, odd within odd, even within odd. So you've got 4 cases. Let's do each one in turn. Now I might want to shrink this a bit to, in fact, rather than shrinking it, let's, we don't quite need all of that space. That's a bit much. There we go. So let's lose this because it's not really going to be relevant necessarily. Oh, let's start there. So here we have what? An example of the odd within odd case. So 11 numbers, 1 in the middle, 5 on either side. So for the quartiles, we do not use the middle one. We do not use the yellow one. So 1, 2, 3, 4, 5. These are the numbers. I don't know if you're actually seeing those highlights and so forth. But if you are, those are the numbers that we use. 2, 4, 5, 7, 8. Those are the numbers that we use for Q1. It's an odd number of them. So that will be our Q1. So there's our median, and there's our Q1. Likewise over here, 1, 2, 3, 4, 5. Don't use the middle one, the 10 I mean. So 5 of them, and there's our Q3. Now again, there's 11 numbers, so the quarter point of 11 numbers, the halfway point even of 11 numbers, are not going to be terribly precise, right? But in the back of your mind, picture very large sets of numbers with not so many repeats. If you've got 1,000 numbers, then what's going on here? Lots and lots of numbers, 1 or 2 at the quarter point. Lots and lots of numbers, 1 or 2 at the halfway point. Lots and lots of numbers, 1 or 2 at the three-quarter point. Lots and lots of numbers again. So the 2 and the 4 are doing the work of a full quarter-ish of the list, on the order of 250 out of 1,000 numbers, let's say, and so forth and so on and so on. Obviously, for 11 numbers, whether you count this or not, like we said, but for very large sets of numbers, these concepts are much more accurate. If you've got 1,000 numbers, nobody's going to notice the absence of 1 or 2 at the join there. So this is the way things play out in the odd within odd case. Q1 is the first quartile, 10 is the median, the second quartile if you like, 20 is Q3, the third quartile. And again, don't forget to put them in order first. So loosely speaking, a quarter, there's only 11 of them, so it's not very precise, but loosely speaking, a quarter of the numbers, 1/4 of the 11 numbers, 250 of the 1,000 numbers, whatever, 25 of the 100 numbers. 1/4 of the numbers are less than Q1. For very large sets of numbers, we can be pretty free and loose with less than versus less than or equal to, so don't worry about that. Half the numbers are less than 10. 3/4 of the numbers, that is 75%, are less than 20. This brings us to the concept of the 5-number summary. The 5-number summary is just a way of representing these ideas. I think I'm jumping the gun a bit here, but as long as we are talking about it, we may as well finish it off. So we have the concept of the 5-number summary. In the obvious order, that's going to be the minimum number in the list. Let's write that out. Min, Q1, median, Q3, max. The simplest, the absolute simplest summary of a set of numbers that is worth a damn is a notion of center and a notion of spread. Let's think about that. The average human being has 1 ovary. The typical human being does not. If you average together billions of zeros and twos, you're going to get 1. The average human being has 1 ovary, but no particular human being necessarily has 1 ovary. So it is just as important to know how how spread out around that center you are. So the simplest notion of the simplest description that is worth a damn of a set of numbers is some notion of center followed by some notion of spread. Uh, any the center the Either center, whether it's mean or median, by itself is not necessarily very useful. Like I said, the average human being has one ovary. The median human being has one ovary for that matter. But what does that tell you? Absolutely nothing. How much more or less than one does your typical human being have? That's just as important. So you need the spread in order to give some context to the center. The simplest summary of a set of numbers that's worthwhile is two numbers, the center and the spread. Something that is not quite as simple, the next simplest thing would be the 5-number summary, and this is solely in the order scheme of things. So it preserves a little bit more information than just the center and just the spread, but of course the nature of any summary is that you're going to lose information, right? We've already talked about that when we were turning sets of data into frequency tables and histograms and bar graphs, right? Oh, well, not so much bar graphs. So, yeah, you're always going to lose information when you're summarizing, but you can only hope that what remains is worth studying. So, the 5-number summary is the second simplest way that you can summarize things. The minimum number in the list, the Q1, the median, the Q3, and the max. Oops. Notice, by the way, that these are not evenly spaced. That's the whole point, you know? Let's say that these are heights of bushes, feet. What kind of increase is there from the 0 point in the list to the quarter point in the list? There's an increase of 3 feet. What kind of increase is there from the quarter point in the list to the median in the list? Well, there's an increase of 5 feet. What kind of increase is there from the halfway point in the list to the 3/4 point in the list? There's an increase of 10 feet. What kind of increase is there from the 3/4 point in the list to the max of the list? There's an increase of 8 feet, or gallons, or degrees, or whatever. So you can see the asymmetries presenting themselves. The distances between those numbers are not the same. So you can see the asymmetries. You can see the lack of uniformity, if you like. Second example. Let's see. Let's add a couple more columns here, and make those about the same. What am I using? 6. Come on. Oh, it is 6. Okay, let's take it down to about 5. There we go. Still visible, but a little easier. So, what do we have here? An odd within odd scheme. Let's lose the highlights and start over. Okay. So that was an odd within odd scheme. Let's throw on one more number here, 29, and do this again. So now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we have an even within even scheme. So now we have 1, 2, 3, 4, 5, 6. Double check. 1, 2, 3, 4, 5, 6. So there you go. I've lucked out, numerically speaking. The medians have all been ones I can do in my head, but In the even case, the median is the average of the middle two. So 10 plus 12 divided by 2, 11. So now the median is 11. Now again, remember that in the even case, everybody gets used. In particular, the 10 gets used for the small half, and the 12 gets used for the big half. So here we have the even within an even scheme. 6 numbers, still even. So what am I using here? Orange? No, that's not what I want to do. So 6 numbers, the middle two of those 6 numbers will be our, whoops, I centered them, didn't I? So there's not going to be a nice way of doing that. There you go. So 6 numbers on the small side. The average of the middle two is the Q1, the median of the small half. 5 plus 7 divided by 2. So that's 6. And likewise, on the big half, we've got also 6 numbers. So it'll be the average of the middle two. What does that give us? 20 plus 25 divided by 2 is probably 22 and a half. Yes. Now bear in mind there's only 12 numbers, but 12 is divisible by 4, so it's literally true that a quarter of the numbers are less than 6, and half the numbers are less than 11, and three-quarters of the numbers are less than 22 and a half. Now, granted, there's nothing you can say about 22 and a half there that you can't say about 23 or 24, but this is the way we compute the median in this course. So, loosely speaking, we say three-quarters of the numbers are less than 22 and a half. And of course, the min hasn't changed, and the max is now 29. Well, let's see. If we just keep throwing on numbers, then we should cover all 4 cases there. So case 3, first of all, let's lose our highlights. And now we need new answers. Well, most of these. This is still going to be 2. So now we have what? 1, 2, 3, 4, 5, 6, 7. Try again. We're not going to need this probably. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 6, 6, 1, right? 1, 2, 3, 4, 5, 6. The next one. Median's in yellow. Whoops, not that yellow. Still not that yellow. This yellow. Double check. 1, 2, 3, 4, 5, 6. The next one. So there you go. So now we have an even within odd scheme going on here, right? Why is this not bolding? There we go. So these numbers over here in bold will get used for Q1. These numbers will get used for Q3. We still have an even number when we go to compute the quartiles. So the average of the middle 2, the average of the middle 2. So our min is still 2, and our max is now 32, and our median is 12. 5 plus 7 divided by 2 is 6, and 25 plus 28 divided by 2 is 26.5. Now again, there's 13 numbers, so the halfway point and the quarter point are not real things actually. But loosely speaking, a quarter of the numbers are less than 6, half the numbers are less than 12, 3/4 of the numbers are less than 26.5. So there is the even within odd scheme. And if we throw on one more number here, then we ought to theoretically be able to do the last scheme here. So let's again lose all of our formatting here and start over. Well, that's still going to be 2. And now the max is going to be 35, of course. And let's see what we got. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 7 and 7, right? 1, 2, 3, 4, 5, 6, 7. So there is our, whoops, did it again. There's our one guy. Yellow for the median I've been using. 1, 2, 3, 4, 5, 6, 7. So there's the other contributor to the median. So let's throw on that middle column again there. That's just a kind of a divider. So our median now is going to be 12 plus 16 divided by 2. 12 plus 16 divided by 2, which is 14. So now there's our median. What have we got here is the odd within even scheme, right? The only one remaining. So we have 1, 2, 3, 4, 5, 6, 7. The 12 gets used. So 7 numbers. So the fourth one in from either side will be our Q1. And likewise over here, counting the 16, we've got 7 numbers. Even case, use the guy. So 1, 2, 3, 4, 28. 1, 2, 3, 4, still 28. I got it wrong twice, so this is why we double check both ends, remember. So there we go. So now Q1 is 7, and Q3 is 28. So there are all 4 cases. Odd within even. Which one is this again? This is odd within even. So that gives you an idea of how you do all 4 cases for computing the quartiles. Quartile rules do come down to 2 things: how to compute the median, middle one, or average of middle 2, odd case, even case, and exactly which numbers to use. In the odd case, we don't use the middle one. In the even case, everybody gets used, each of them for their respective halves. And we did talk about the 5-number summary. So while we're here, let's just finish this bit off. 5-number summary: the min, Q1, median, Q3, max. Okay, that's on both pages, but that's okay. Now, as for spreads, there's a couple things you can do. Our book talks about the range, which is the max minus the min. Nobody really uses the range too much, unless there are occasions where you want to know the full extent of the data, you know, from the absolute smallest case to the absolute biggest case. Everybody has to be able to fit through the doorway, whatever. It does have limited usefulness because, of course, the max or the min could both be very exceptional. You know, the heights of 99 gorillas and 1 King Kong, as I said. There's an outlier for you. The max versus the min, the maximum height versus the minimum height would not be terribly helpful in a case like that. It would basically be approximately the height of King Kong, right? The interquartile range, the IQR, on the other hand, is much more healthy. So for the order scheme of things, the notion of spread that goes along with median as center is the interquartile range. It's a bit of a mouthful, but it's exactly what the name implies. It is the distance between the quartiles. So it is Q3 minus Q1. Let's just look at this one example here. So the IQR in this case is going to be Q3 minus Q1. So 28 minus 7 is 21. What does the IQR represent? It represents the increase in the middle half of the list. Remember, we're talking about however many numbers. Let's say 100 numbers. Then you're talking about from number 25 to number 75. From the quarter point in the list to the three-quarter point in the list, what kind of increase is there? In other words, the middle half of the ordered list. There's an increase of 21 feet or gallons or degrees Fahrenheit or whatever it is. So that's what the IQR represents. Now let's think about that. Is it up to specs for a spread? Well, let's get a little bit creative about this. We'll talk a little bit more about unit changes later. But let's say that this number is 2, 4, 5, 7, etc., like you see them. Then the IQR is 21, right? On the other hand, let's say that this number is, let's tinker with our units a bit. Let's say that this number is 2,000, 4,000, 5,000, 7,000, 35,000. Well, then pretty clearly this is going to be 21,000, right? Put it another way, everything we're computing is in the same units you started with, even if it's thousands of turnips, whatever. So, in other words, if every one of these numbers were 1,000 times bigger, then this would be 1,000 times bigger. Well, if these numbers are 1,000 times bigger, then numerically speaking, they're a lot more spread out from one another than if they're just 2, 4, 5, 7, right? So, the thing that tells you how spread out they are is a lot bigger. I did not like that first quote, did it? Or am I just losing it? It's just not fitting, that's all. There you go. Let's play it the other way. Let's say that this is 2 millionths, 4 millionths, 5 millionths, 7 millionths. Then this is going to be 21 millionths, 21 over a million. In other words, very tiny, a lot smaller. Now, if this is 2 millionths and this is 35 millionths, then the bottom line is the numbers are a lot more clumped up than they were as you see them on the screen, right? So the thing that measures how spread out they are, 21 millionths, is a lot smaller. So yes, IQR is up to specs for what we said in the first place that a spread should represent. That it should be a number which is at least 0, can't be negative, and the more spread out the numbers are, the bigger it is, and the more clumped up, the less spread out the numbers are, the smaller it is. So it is up to specs in a general way for what we call the spread of a set of numbers. On a related note, bear in mind this can't possibly be negative, right? Q3 has got to be at least Q1. I'll let you think about, it's certainly plausible that Q1 and Q3 could be the same. Think about what happens if you have a lot of repeats in the list. Play around with that in the homework problems. If you've got a lot of repeats in the list, then it's certainly possible that Q1 and Q3 could be the same, in which case this is 0. But it can't be negative, right? Q3 has got to be at least Q1, or you forgot to order them before you began. So there's no way that Q3 minus Q1 can be negative. There's no way that Q3 can be less than Q1. So it is a non-negative number. It's at least 0. And the more spread out they are, the bigger it is, the less spread out they are, the smaller it is. Now remember, everything in the order scheme of things leaves you a lot of room to maneuver. Nothing you see on the screen except the maximum is going to change if I make this some other number that is at least 32, or in fact, at least 28. Right? Literally all it does is change the maximum. So everything in the order scheme of things, remember, only cares about relative placement in an ordered list. Everything in the order scheme of things, including IQR and all these 5-number summary things, except min and max, of course, are not affected by outliers. The quartiles, the median, the IQR, they're not affected by outliers. Obviously, the maximum is affected by outliers. It is an outlier. If there is an outlier, the maximum will be one. So, advantage order scheme of things, they're resistant to the effects of outliers, extremities, long tails. Remember, visually speaking, the quartile is the place where a quarter of the area of the histogram is to the left. The median is the place where half the area of the histogram is to the left. The third quartile is the place where 3/4 of the area of the histogram is to the left. Think of that visually. As far as the median goes, let's take a simple example. Well, maybe not. As far as the median goes, this line here, you can bunch up this area. You can take this area on this side of this line to the no, we're looking at the median line, remember. You can take this area to the right of the median line and you can spread it out thinner and longer, and it's not going to change the median. As long as no area crosses that line, it's not going to change the median, but it will drastically affect the mean where things balance. Likewise, if you clump up this area on this side of the median, really tall and thin here, as long as no area crosses that median line, this is still going to be the halfway area point. But again, it will drastically affect how it balances. And the same is true of the quartiles and so on and so on. So that's basically everything about the median scheme of things, with one exception. We want to talk about outlier rule. This is a rule of thumb for detecting outliers. It is only a rule of thumb. In other words, if you want to, for most reasonable sets of data that you're likely to encounter in the real world, it will correspond pretty closely to your intuitions about what is outside the general pattern. An outlier, remember, is an individual or individuals that are outside the general pattern. General pattern should tell you what you need to know. Subjective, human judgment call. There is no substitute for that. There is no substitute for human intuition when you're talking about something as vague as the general pattern and whether you're outside it. So that is not the kind of question that's going to give you a mathematical answer. However, the outlier rule of thumb says that for most reasonable sets of data that you're likely to encounter, the following rule corresponds most of the time to your intuitions about what you would consider to be outside the general pattern. So don't think of it as a rule for detecting outliers per se. Think of it as a rule of thumb for detecting outliers. Think of it as how the rule detects outliers. But again, there's no substitute for human intuition. Anyway, what is an outlier? An outlier is an individual that is either a lot bigger than the others, or a lot smaller, more negative if you have to, than the others. So in other words, outliers are individuals that are a lot bigger than Q3, way over here, or a lot less than Q1, way over here. Question is how much? How far do you have to go beyond Q3 or beyond Q1? How much do you have to add to Q3 or subtract from Q1 before it's considered to be suspiciously far away? The rule of thumb says it's 1.5 times the IQR. So that is the principle. Oops. Something is considered an outlier if it's more than 1.5 times the IQR added onto Q3, or 1.5 times the IQR subtracted off of Q1. Let's take our example. So all this should still be right. So maybe over here, Q3 plus 1.5 times the IQR. Maybe make it a capital Q because it's freaking me out. Or Q1 minus 1.5 times the IQR. What happened? Oh, let's see. Let's left justify this stuff. Oh, it's in the wrong blank. That's one of my problems. Well, I'll leave it there. So what is 1.5 times the IQR? Whoops. It doesn't seem... So 21 times 1.5 is 31.5. So here we're talking about 28 plus 31.5. And here we're talking about 7 minus 31.5. 28 plus 31.5 is 59.5. So if there's anything in the list bigger than 59.5, it's considered an outlier. 7 minus 31.5, I'm pretty confident without computing that there is nothing smaller, more negative, in the list than that. So if there's anything in the list bigger than 59.5, it's an outlier. If there's anything in the list smaller, in the number line sense, more negative than 24.5, it's an outlier. Well, there is nothing that small in the list. There's nothing negative in the list at all. But there isn't any outliers on the other side either. So there are no outliers in this list, right? And that pretty much corresponds to what you're seeing as you look at the numbers. On the other hand, if this number was a 70, bear in mind, if I make that a 70, if I replace that biggest number with something else, which is at least 32, it's not going to affect any of these calculations, right? Except, of course, for the max. So all of this is still true, and this is still the cutoff point, and now there is an outlier in the list. 70 is an outlier. Of course, if you replace this with a 70, an 80, and a 90, then that won't affect any of these calculations. So theoretically, you could have 3 out of 11 things, 3 out of, was it 13? 3 out of 13 things outside the general pattern. Well, guess what? 3 out of 13 things, 23%, 3 out of 13 things are not outside the general pattern. 3 out of 13 things are part of the general pattern. You can't have that high a percentage of outliers, of course. It's only a rule of thumb. Remember, if you want to screw with it, you can find ways. So theoretically, and the same thing is going on the other side, of course. If this were negative 30, it would be an outlier. If this were negative 100, negative 70, negative 30, they would all be outliers. So theoretically, if you really want to screw with it, the rule of thumb could detect almost half the data as being outliers. For a case like that, of course, it is not corresponding to any kind of intuition for what's outside the general pattern. It's only a rule of thumb. You could certainly screw with it if you want to. There's any number of ways that you could make the outcome of this computation be at odds with your intuition for what's outside the general pattern. Another way you can do it is to create an artificially big valley in between, like have a big peak followed by a big peak followed by a whole lot of nothing followed by another big peak. That'll make the IQR kind of artificially big. So there are ways you can screw with it if the data is weird enough. And bear in mind, these principles make a lot more sense for large sets of numbers. When you're talking about 13 numbers, you're on somewhat thin ice even in talking about the general pattern, right? But nevertheless, that's the principle. And again, while we're here, if there's anything in the list more negative than this, then it would be an outlier on the small side. So there isn't. But if this were a negative 30, it wouldn't affect any of these calculations, except, of course, it would change the min, but that doesn't affect any of this. It wouldn't change Q1 or Q3, which is all we're using at the moment. So now there is something that's an outlier on the small side. Okay? So there's the outlier rule. Something else we can do with the outlier rule. Let's stick with what we got on the screen here at the moment. So 70 would be an outlier, 62 would be an outlier. Again, I can replace this number with anything, which is at least, let's say, 32, 28 in fact. And it won't change any of these calculations. It won't change the cutoff point. So the 62 would be an outlier. The 60 would be an outlier. The 59 would not be an outlier, right? It's a little bit different from the others, but it's not different enough from the others for the outlier rule to consider it outside the general pattern. So now bear in mind that there is, when you are talking about things that are this vague, I mean the mathematical rule is very precise, but outside the general pattern in human terms is pretty vague. So when you're talking about things that are this vague, there's always going to be gray area, right? If you want a hard and fast rule, if you want a hard and fast cutoff point for what is outside the general pattern, then a hard and fast cutoff point you are going to get, right? What is the difference between a 59 and a 60? Not a lot, but the one is pegged as an outlier and the other is not. What is the smallest number we could put here and have it be considered an outlier? Now again, there's no point in splitting hairs when you're talking about things that are this precise. But if we are being technical about this, and we are, I did say more than. I did say less than. A tie does not count. So if there were a 59.5 in this list, it would not be considered an outlier. It's got to be more. But if there were a 59.51, then yes, it would be considered an outlier. What's the difference between a tree that's 59.5 feet tall and 59.51 feet tall? Not a lot. But the one is an outlier and the other is not. And of course, I could do this all day. Only I need more space. That's an outlier. That's an outlier. So you see, there is no smallest possible outlier. If the actual cutoff point itself does not count, then you give me anything bigger than that, I'll average it together and give you something smaller that's bigger than that. I can do that all day. I can throw on zeros for the rest of my life here. There's always going to be something smaller that would be called an outlier. So there's no smallest possible outlier. But what is the smallest whole number that would be considered an outlier? Replacing whatever it was, I forgot what it started as, 30-something. Replacing that number with what number results in the smallest possible whole number outlier? Well, again, a 59 is not an outlier, but a 60 is. So a 60 would be the smallest whole number that would be considered an outlier. In other words, bump it up to the next whole number. Now again, remember, a tie doesn't count. So if you're looking for the smallest possible whole number outlier on the big side there, then just go to the next whole number after this guy. Whether he's a whole number or not, just go up to the next one. If this is a 57, then this would be a 58, and so forth. So that'll be handy for the homework. Well, let's see. So that's everything to do with the order scheme of things, and we're coming up on 50 minutes. So we'll do standard deviation in part 3 of section 2. It's one of our longer sections. And after that, we'll talk about the effects of unit changes. I'm still kind of going back and forth on whether to make that 2 videos or 3. As I upload part 1, I'm saying part 1 of 4. So I'm gambling that there are going to be 4 videos here, but we might be able to squeeze the rest of section 2 into the next one. We'll see.